Okay, so now we need to talk about how do stars that are more massive in general than 8 masses of our sun, 8 solar masses, how do they live their lives? How do they end their lives? And remember that they live their lives more quickly. So kind of from left to right here, we see some familiar stages, like they start out as a protostar, they end up arriving at the main sequence where they're fusing hydrogen into helium in their core. Notice that these main sequence stars that are massive will be blue in color. Then they'll leave the main sequence and go up into the red supergiant stage. Then this next caption over here says that they will go ahead and reestablish burning in their core now helium into carbon. We talked about that with lighter stars too, didn't we? Just to kind of skip a few stages, over here, the second to the last stage actually is supernova. Who doesn't love a good star blowing up? So these massive stars will end their lives in this violent event we call a supernova. Then what's left, over here, this tiny little dot, actually the star blows up, but what's left behind intact is the core. And the core of that massive star will either be a neutron star or a black hole. So we said that massive stars, although they have more stuff to burn, when I talk about burning, I'm talking about nuclear fusion, they have more material to burn in their core, but they burn it more quickly, and part of the reason they burn it more quickly are these higher temperatures. And at these higher temperatures, the fusion rate is faster. And kind of related to that, we have this thing called a carbon, the presence of carbon atoms, nitrogen atoms, and oxygen atoms in the cores of these stars can make the fusion rate go faster. These atoms of this type actually are acting as what we call a chemical catalyst. And catalysts in a chemical reaction like this are not consumed. They're just they help facilitate things moving faster. So notice that actually with this cycle, the important thing I'm showing you is that hydrogen is being converted to helium, but it's being catalyzed. It's being converted more quickly. And this again happens at these higher core temperatures that you have with these more massive stars. So massive stars, they start out as protostars. They arrive at the main sequence on the HR diagram. They are fusing hydrogen into helium. They will run out of hydrogen in their core to fuse to helium. They will begin contracting, and then they'll start outside the core region. They'll start fusing fresh hydrogen and helium, this thing we call shell hydrogen fusion. At that point, they will have left the main sequence on the HR diagram and be in the supergiant region. They will reestablish then, just like low mass stars, they will begin as they have contracted and heated up their core to the point where they can go ahead and begin fusing helium into carbon. So this is a periodic table. These numbers here mean the number of protons in an atom of that particular type of element. Okay, so we say that with nuclear fusion, we get heavier and heavier elements. We get more and more protons in the nucleus of these atoms, and so we get a different element. So just to kind of show you here, I've highlighted helium, has 2 protons in its nucleus. Carbon has 6 protons in its nucleus. So the carbon, nitrogen, oxygen catalysts up there I'm highlighting them. They can make the hydrogen fusion in the core of high mass stars go faster. So with the higher temperatures, when helium does begin to fuse, actually the presence of helium, we can get this phenomenon, this nuclear reaction, where we get heavier elements. For instance, I'm showing helium and carbon, a nuclear reaction going to form oxygen. Now remember, with all of these nuclear reactions, we get a bunch of energy released too. Notice helium can combine with oxygen to form neon, and helium can combine with neon to form magnesium. Okay, again, this is a phenomenon that can happen in those massive stars at higher temperatures. So helium capture builds carbon into oxygen, neon, and magnesium. And a little bit later, I have a slide that kind of shows we definitely have the abundance or the amount of the different elements that are out there in our universe are a function of what is favored with regard to nuclear fusion. Advanced nuclear burning. You know, I'm not going to test you over this, but I did kind of want to include it in my notes this semester. So we can get the formation of silicon from carbon and oxygen, the formation of sulfur from oxygen, 2 oxygen atoms. Okay, the formation of iron then from 2 silicon atoms. So these are all nuclear reactions. And we're going to see that iron there, iron that has 26 protons, and a typical iron atom in its nucleus will have 30 neutrons for a mass number of 56. That's basically as far as nuclear fusion will go in the cores of stars. So just to kind of highlight those elements I mentioned on the periodic table. So notice we have a lot of gaps between those elements. And again, maybe the gaps will be where we are less abundant, lower amounts of those elements in the universe. So I like this animation. I think it does a good job. It's going to show you high mass stars. So, let's see. Wait till I show some captions. Notice, it's still running. So can you kind of see the onion sort of structure we have with, in the core we have the hottest temperatures, and we're fusing higher and higher mass, higher and more complicated, heavier and heavier elements. And then outside that we have shell burning regions. And actually where I've stopped it here, we have gone ahead and the core is not actively fusing anything. It's inert oxygen core. We have shell carbon fusing outside that, helium fusing shell outside that, and a hydrogen fusing shell outside that. So let's go see what happens next. Notice kind of the variability of the star. And we have more and more different types of shell fusing. And then in the core here, this says inert iron core. So basically silicon has fused together to make this element iron. And iron will not, and I have a slide coming up to kind of show you, but even though the core of that star or that star will contract and the core of that star will heat up, you're not going to fuse iron like this. So this says death of a high mass star. We'll go ahead and warning, fusion of iron will not give off energy. Well, that was kind of anticlimactic, but that little that was your supernova event. And then this little dot up here says it's either going to be the core that's going to be left up that doesn't blow up is either going to be a neutron star or a black hole. And down here, actually, we have something called a supernova remnant down here. Now, that's pretty good. So iron is the heaviest thing that in the core of a star that it will form. And it will try to go ahead and fuse iron, but I don't know if you can see this. It basically says that any element heavier than iron, it fusion actually will require energy, and to release energy you need to do some sort of nuclear fission, and we talked about fission is actually the splitting of a nucleus. So a few slides ago I kind of showed you where helium, we have this helium capture that can go on in the cores of massive stars where the temperatures are really high, and helium ends up with kind of this we have an optimum sort of situation of forming certain elements are favored, and so those certain elements are more abundant. So I'm not necessarily going to show you this animation because it's the same animation as we saw before, but just know that massive stars at the end of their life, before they go supernova, they have this sort of onion sort of layers to them, and the core is iron. So during the supernova, during the explosion part, actually what happens is that electrons, like this says, electrons will combine with protons. I know it sounds kind of strange, but we got a lot of force here, a lot of gravity, high density. Ultimately, there is a falling inward, basically, a little bit of a collapse where electrons combine with protons to make neutrons and neutrinos. And as I said, that object, that crazy little core of that massive star that's left over is not iron anymore, but following the collapse, basically, it's going to be either a neutron star or a black hole. And we'll talk more about neutron stars and black holes in the next chapter. So during this explosive supernova event, we have a fair bit of energy that can create kind of like, I would say kind of knits, sort of little compression areas in the, during the explosion. And we can have actually, we call them nucleosynthesis. We can have heavier elements formed. So supernova remnants are very pretty. So supernova remnants, this is an example of the Crab Nebula. I believe it's Messier object number 1. And so basically this is the guts of a star, massive star that blew up back in the year 10,054 AD. So, and it was recorded from back then. So let's take a look at that region of the sky in different wavelengths. So this is the visible image. Let's look at infrared. Ooh, ah. Let's look at radio. Isn't that pretty? Let's look at X-rays. It's my favorite. Okay, and can you kind of see a disc sort of thing? And these looks like jets kind of poking out. Well, that's because we have a neutron star hiding in that mess. Okay, so the star blew up and it created that thing we call supernova remnant. And in the center, though, the core actually is this object we call a neutron star. And like I said, I'm looking forward to talking about that in the next chapter. So we have a supernova event that happened kind of recently in 1987. So this is the sky before the supernova event, and this is the sky during the supernova, or shortly after the supernova event. So it actually now has faded, but it would be pretty bright for a couple weeks.